welcome back to the mezzanine stage. If you haven't met us already, my name is Megan, and I'm on the design team at Figma.
And I'm Rachel. I'm on the engineering team at Figma. We hope you had a nice, quick recharge, got the coffee break, got the stroll, blood back moving around, because we have a lot of great talks in store for you this next set.
Kicking us off, we have Ringley from Boston Dynamics, who's working on a design problem that might sound like the start of a Black Mirror episode, but is actually an incredible UX challenge.
That's right. We're talking robots, people. Brian's going to talk us through his design process for designing interfaces to teach robots about the world. So please give a warm welcome to Brian.
The Black Mirror reference. Never gets old. This is Atlas by Boston Dynamics, a generally capable humanoid robot, a doer of things, the product that can do anything. Almost anything. I didn't mean to gaslight you into coming into this presentation with a disingenuous title, but the focus right now is on industrial applications. Every design decision we've made, everything that I'm going to show in this presentation is predicated on making Atlas do real factory work. So if you're in my circles, you're either working on a humanoid robot and it is the only viable way forward for robotics, or you're not, and you think that they're an over-engineered solution in search of a problem. The truth is that a lot of the things we're applying humanoids for today, the types of applications where we're trying to fill these automation gaps, could be done with traditional industrial automation. It's just that it's not economically viable to solve every application project with a bespoke piece of hardware. By making a single investment in a humanoid, in an Atlas robot, and then programming everything with software, you basically turn every application problem into a software problem. The humanoid robot isn't a technology breakthrough, it's an economics breakthrough. So it's good for the customer that it's just a software problem. For us as designers at Boston Dynamics, we're still dealing with both. We have to make some kind of robotic morphology that's capable of interacting with the world in all sorts of ways we couldn't possibly predict, but we try to generalize as best as we can. But we also have this generalized software problem, which is a little bit of a weird problem. We have to create some kind of general behavior skill set that goes on the robot so that it can actually do things. We have to allow you, the user, to communicate what skills you want with the robot. And then you still probably want to assemble all of that into kind of traditional and repeatable applications in the industrial environment. So, no big deal. So we'll start with the hardware piece. One of the very first design questions we asked was like, does it need a head? I don't know. Like, question everything. Maybe it doesn't. There's a lot of advantages to bringing the robotic perception, the cameras in the head, up to eye level. I mean, we're trying to tackle human purpose tasks in human purposed environments, so that makes sense. But we have 360-degree peripheral vision around the head. So why does it have to have a face? Why is there directionality? Why do we have this axis? Why do we have this degree of freedom? What's the point of that? Well, the point of that is that this robot doesn't exist in a vacuum. We're putting it into the real world with you. It's supposed to be in a factory space, interacting with workers. And how do you communicate? We look at each other's faces. So if you approach a robot and that robot looks at you, you get the sense that it recognizes your presence and that it will behave correspondingly, safely. If the robot looks at a workpiece as it's doing some kind of automotive task, you get that predictability. You anticipate its next movement. So the face matters. So we've got a head, 2 arms, 2 legs. This is the classic humanoid form. But it doesn't look like a person. This is intentional. We're not trying to trick you. We don't want you to think this is a person. We want you to look at the Atlas robot and think, this is a piece of industrial automation equipment. This is a useful tool. That's a big driving force behind our design decisions. And also, why would we limit ourselves to the capabilities of the human body? This is the whole fun of working on machines, is that they can do things that we can't do, that together we can achieve stuff that we couldn't achieve before. So we want the robot to have superhuman strength, mobility, dexterity, flexibility, range of motion, perception, and etc. This isn't our first rodeo. We've commercialized a few robots before. We have the Spot quadruped robot that's doing a lot of industrial inspection work in manufacturing. We have the Stretch robot that does a lot of warehouse logistics work. And we know that it doesn't matter if you build best-in-class hardware if you don't also solve these other customer problems, which is make it cost-effective and make it reliable. Well, how do you tackle those problems? You simplify, simplify, simplify. You repeat, you use symmetry, you modularize. You'll notice that part of the aesthetic of this robot stems from the fact that in the body we only use two different actuators, so all of the joints look the same. An upper limb and a lower limb don't look that different. An arm doesn't look particularly different than a leg. This helps us just swap out components and just have a simpler thing to manufacture. And there isn't really a notion of a front with the limbs, too. You can invert elbows, you can invert knees. All of the joints rotate infinitely, and it allows for the robot to take whatever the most efficient motion is for the task at hand and also produce emerging behaviors. And all of that is now something that you can build on with software. So who are our users? Well, we have a software platform called Orbit. It allows you to manage your industrial applications that are powered by Boston Dynamics robots. So our users want to be able to retask these robots across that interface. But traditionally, things have been a little bit more locked down than that. This robot does this task, that robot does that task. It's very workflow-oriented. It's a very predetermined set of things. And this is kind of a long trajectory of software, right? You have a couple different user personas. You have your author, who's in something traditional like an IDE. That's their software environment. Then they produce something that an end user uses as a separate environment. Over the last several decades, we've had all sorts of experiments in low-code and no-code interfaces. This starts to blur that user persona between author and end user. And more importantly, it starts to put the extensibility into the context of the application. Because what we really have here is an application scaling problem. OK, great, you solved the software platform. We can do everything in software, but now I need to make 10,000 different software applications. So how do you solve that? Well, you might have heard, but you can talk to your software now. It'd probably be really weird if you went to a config talk and someone didn't mention that. So there is no longer really any meaningful distinction between an author persona and an end user persona. And any application context becomes infinitely extensible. It's a really weird concept, which is any application becomes capable of doing anything. So if we look at how this works on robots today, which is a big assumption, right? I'm like, well, if you can talk to your software and you can do all this agentic stuff, why can't you do that on a machine? How hard could that possibly be? You have a few things here. Like traditionally, Atlas is a project that's been going on since the MIT Leg Lab at the 80s. The Atlas project itself started properly in 2013. I've been working on the commercialization of the electric Atlas model over the last several years. And when I sit down and I use Figma, we use it too. I'm just like you. We do things where we're like, I want to monitor the health of my fleet. I want to make sure that my robots are online, that the network is working. I want to make sure that this robot is where I think it is. And I want to make sure where this other robot is where I think it is, and that it's doing the right thing. So again, it's very prescriptive. You're basically just monitoring kind of a pre-canned recipe for an application. And none of that stuff works anymore. You basically just go into your Figma workspace and throw all of it away because we have to invent new types of software. So where do you start? It has two legs, like us, so it has to stay balanced. So we start there. We start there and we say, we're going to give you a motion example. We're going to use reinforcement learning. We're going to simulate that many, many, many times until the simulation matches the motion example. We're going to transfer that to hardware. And 100 times per second, the robot's going to check the state of its actuators, and it's going to predict its next state. And you're going to get things like natural walking, mobility. You're going to get things like backflips. Because why spend your one precious life working on robots if you don't get to make them do backflips? That's not enough, right? You're, okay, yeah, cool, your humanoid can stand up. Good job, Brian. So you have to build skills on top of that. You have to be able to, in particular, figure out how to leverage dexterous manipulation. So you're like, okay, I'm taking whole body mobility, I've got that, and I've got to combine that with manipulation capabilities. So a lot of this is really kind of centering on the hand. I want my robot to be able to understand that it needs to pick this part from this location, create a grasp, convey it to another location, and place it. The whole world is, our reality is just a series of picks and a series of places. And the way we train this is with behavior cloning. So you have an expert demonstrator, a person, do something many, many times. You use that to train a model. You deploy that to policy on a robot. And provided that it's in a similar environment and it's been demonstrated some kind of skill in that environment, 30 times a second, it's going to be like, what am I seeing right now? What's the state of my body? And it's going to take the next statistically likely set of actuator moves. It looks like the robot has some sense of what it's doing, but it has no semantic knowledge of what it's doing. That's actually a problem. We need the robot to understand what it's doing because we still need to talk to it. We still need to get to that upper level. So, the robot needs to know what is a supplier parts container. It needs to know, I need to grab this part from this container. I need to grab this other part from this other container. It needs to know what it means to grab a part 3 times or to grab a part 4 times. It needs to understand how to handle what are called task exceptions. If I drop a part on the ground, I need to take that out of production, so I need to know what to do. All of this stems from a relationship between these language models, visual language models, which are able to look at images and kind of associate those semantically with the language commands that you've given, visual language action models, which then use that to pass that information on to the models of the behavior policy, and ultimately enact that behavior. So it's agents all the way down. But if we shipped you this product, there's like all this complexity, and we ship you this product, and we're like, well, all it does is automotive sequencing right now, right? We have to start somewhere. The more you demonstrate, the more generally capable the robot becomes. So what you have to do is demonstrate more stuff. This has pushed us from the comfort of the web application space to virtual reality. So as a demonstrator, my goal is to embody the robot. The more that I forget that I'm me and think that I'm the robot, the more natural my task motions are and the higher quality data we have off of that robot to train those behavior policies. So I slide on the VR headset, I'm looking at the pass-through, I know my body's here, I know the robot's body's over there, and then I engage. And it should play like some cool sound effect. And you become the robot, so now you have a photosphere of what the robot's seeing around you. That's your VR environment. And it presents a number of interesting UX challenges. So to be clear, this is not me doing the demonstration, but I did consider this as my confit. The shorts are good, lots of squatting when you're doing demonstrations. And you have a headset. You have whole body tracking, you have chest trackers, you have wands, you have foot trackers. It even gets even more complicated if you want to track your individual fingers. You can wear gloves so that you can track that fine manual dexterity. There's a problem with that, though, because now you can't press any buttons. So we're kind of like racking our brains. When every single little motion you take actually moves and controls the robot and impacts the data you're collecting, how do you actually do traditional input? And we're having these weird conversations. We're like, I don't know, maybe you tap your tongue against the roof of your mouth. The robot doesn't have a tongue, so we couldn't accidentally move a robotic tongue. The robot doesn't have a tongue yet. No, just kidding. We're not doing that. We are definitely not doing that. I would like to keep this job. And what that does is that collects all of your proprioception data, right? The robot's sense of where all of its limbs are, and the robot's perception data, what it's seeing, and it creates that pixels to torque model that I mentioned. So that's good. That builds more skills. But again, in terms of your ability to talk to the robot, you're still talking through that agent, right? You have all of those things I talked about, and at the highest level, you have like an agent harness, and you have a software infrastructure, and it makes it automatic, and it makes it repeatable. But at the end of the day, that agent has to understand the world before it can pass that stuff along to the robot's control policy. So we have to get creative there, too. We have to have a way to like test that agent's knowledge about the world and evaluate it. And specifically, its ability to receive a task instruction and to break that down into discrete steps that it can use to then task the robot's behavior policy. So Magnetiles, shout out. Got a lot of nieces and nephews. So again, what I love about these problems is there isn't like an obvious go-to like UI UX precedent for any of these things. So in this case, we're like, yo, what if I was the robot? What if I put a camera on my forehead and then I told the agent that the agent was the robot? But if the agent looks down and freaks out because it sees my arms instead of robot arms, that's okay, just to keep doing what it's doing. And that's literally what you're like putting into a system prompt. Like, you are a cube stacking robot. You might look down and see human arms. Don't worry about that. It's chill. It just keeps stacking the blocks. And that's how we're going to build a policy. And if you have a loving and supportive wife, albeit a slightly confused wife, and you're like reaching over her and you're like, no, pose your arms like this. It's for the Figma thing. So then you can kind of actually test it. And what's beautiful about this is you just have a conversation, you invent this like weird little web app, and we're using this. This is like useful. And I can do this at home. I don't need a robot. I don't need to connect to a sim machine. I don't need to do anything complicated. I'm strapping a camera on my head and connecting to a web application, and I'm flexing this agent and teaching this agent about the world so that level of the system can pass that down to the robot. It's weird stuff. It's not what I expected when I got into robots. And the reason we're kind of like contorting ourselves in all these ways to solve these problems is because we don't have an internet scale corpus of text like what ChatGPT had. Large language models just benefit from the fact that they can consume text data, and it turns out that you can just consume all books ever written in the internet, and you can have these really incredible generative models. Well, that's not quite the case for the physical world. It's a lot more complicated than that. But it's actually a really cool opportunity because you have all sorts of interaction techniques, some of them software-based, some of them creative hardware-based, and you have to mix and match all of these things. This is kind of a classic industry pyramid that says, well, when you're at the top, you have no embodiment gap. The data that you're collecting is coming off of the same hardware onto which you're going to run that policy. That's really high-quality data, but that's expensive data because I need a robot to do it. And I don't want to be using all of my robots to collect data. I want my robots to be doing real things in the real world. So you can go down that stack, and you increase that embodiment gap, but the data gets cheaper. And at some point, we're going to scrape every video frame that's ever been put on the internet. We're going to find every motion, every person, not specifically, but the community is going to find every frame of video that's ever been put on the internet, scrape that, find every instance of every person moving their body to achieve some task, and we're going to have an internet scale model. But that alone won't be enough. You'll have to mix and match these things because the robot's interacting with the real world. There's like tactility, there's interaction, there's stuff that you can't fully understand from pixels. So why are we doing this, right? We're working with, it's a means to an end, really. We're working with Hyundai. We're deploying these robots into these manufacturing facilities. And again, we're finding all of these edge cases where automation is of benefit, but it's not economically viable with custom hardware solutions. The generalized hardware solution turns that into a software problem, makes it economically viable. We start to fill those gaps. And what you'll have is this new breed of like agile mobile humanoids doing these kind of gap-filling tasks. And you'll have traditional industrial automation as well. And all of that will be orchestrated by these high-level factory systems in heterogeneous fleets organized by manufacturing execution systems. And this is the vision of the software-defined factory. The humanoid's a means to an end. It's the robot. It's the factory itself that becomes the robot. One of the awesome things about working at Boston Dynamics is that, as a designer or otherwise, is that you get to participate in changing the public's perception about what robots are capable of. That's like a really powerful thing, to make you think like, oh, actually robots could interact in my life like this. They could do things like this. And we will get there. And we won't get there because it's some like inevitable religious belief I have. We'll get there because it's possible. And we're curious humans. And we're going to find this out. We're going to find how it enriches our lives and what it's capable of. And I want you to think about like everything that you're seeing at Config this year. Every amazing revolutionary thing that's happening with software. And I want you to picture what that means for hardware and robotics in the world. The next time you see me up here, there won't be an asterisk on the talk. Thank you.